Hello everybody, and welcome to our video on combining functions and composite functions. So first we're just going to do some quick definitions of some basic ways of combining functions. So let f and g be two functions. The sum, f plus g, is defined as f plus g of x equals f of x plus g of x. The difference, f minus g, is defined as f minus g of x equals f of x minus g of x. The product, f times g, is defined as f times g of x equals f of x times g of x. The sum, f over g, or sum, that should be quotient, so yeah, go ahead and fix that, please. The quotient, f over g, is defined as f over g of x equals f of x divided by g of x, provided that g of x does not equal 0. So this is key, of course, because we can't divide by 0. So the quotient of two functions is only defined in the case that that bottom function isn't 0. Okay, so let's take a look at this first example here. Let f of x equal x squared plus x minus 6 and g of x equal x minus 2. Evaluate the following. F plus g of 3. Well, this is pretty straightforward. This is f of 3 plus g of 3. So let's look at f of 3. That's 9 plus 3, that's 12 minus 6. So that's 6 plus g of 3, which is 3 minus 2, which is 1. This is 6 plus 1, which is 7. Now let's find f plus g of x. So here, we're just going to take f of x plus g of x. That's x squared plus x minus 6 plus x minus 2. And here we've got x squared, that's the only squared term. Then we've got x plus x, so that's 2x. Here we've got negative 6 plus negative 2, that's negative 8. All done. Now what you can see here is that if you actually plugged in 3 into this function, you'd get 9 plus 6, that's 15, minus 8, which is 7, of course. So in the case where you're evaluating the sum of a pair of functions at a single number, it can be quicker to evaluate each one separately and then write the answer. But if you have to do repeated computations of sums of two functions, then it's going to be easier to just simplify your function first and use that result. Okay, f minus g of 5, that's f of 5 minus g of 5. And what does that give us? That gives us 25 plus 5, that's 30 minus 6, that's 24, minus g of 5, which is 5 minus 2, and that's 3. So this is 21. Okay, so now let's find f minus g of x. That's x squared plus x minus 6 minus x minus 2. So the key thing here is this negative has to distribute here. So this is x squared plus x minus 6 minus x plus 2. That gives us x squared, and then plus x and minus x cancels. And then we have a negative 6 plus 2, that's negative 4. All right, next we have f times g of 2. That's f of 2 times g of 2. So what do we get here? Well, f of 2 is 4 plus 2, that's 6 minus 6, that's 0, times 0. So this is just 0. That was easy enough. Now what about f times g of x? That's f of x times g of x. That's going to be x squared plus x minus 6 times x minus 2. And here we need to distribute every term of the multiplication here. So x times all of these terms is x cubed plus x squared minus 6x. Then we'll distribute the negative 2. That's minus 2x squared minus 2x plus 12. And now we just need to do some simplification here. So we only have one x cubed term. And then we've got x squared minus 2x squared. That's minus 1x squared. And then minus 6x and minus 2x, that's minus 8x. and then plus 12. All right, all done there. Okay, f over g of 1. Well, f evaluated at 1 is 1 plus 1 minus 6, that's negative 4. And g evaluated at 1 is 1 minus 2, that's negative 1. And negative 4 divided by negative 1 is just 4. Now, f divided by g of x is f of x divided by g of x, which is just x squared plus x minus 6 divided by x minus 2, provided that x is not equal to 2. Because if x was equal to 2, we'd be dividing by 0 here. Okay, and now I can actually simplify this a bit further and factor the numerator here to x plus 3 times x minus 2. So that's factors of negative 6 that add up to positive 1. So that's 3 and negative 2. And then I can cancel these and say that this is equal to x plus 3, provided that x is not equal to 2. So this is something we really want to be careful about here, right? These functions are only the same when x is not equal to 2. And that's because x minus 2 divided by x minus 2 is 1, and multiplying anything by 1 doesn't change it, but we can't divide by 0. So if we still have this factor in the denominator here, 2 is not a valid member of the domain. So these two expressions, again, are equal only in the case that x is not equal to 2. All right, well, that's it for that example. Let's go ahead and move on. And we're going to find the domain of some functions, f plus g, f minus g, f times g, and f divided by g for f of x equals the square root of x minus 3, and g of x equals the square root of 9 minus x. Now, the thing to keep in mind here is that for f plus g, f minus g, and f times g, the domain is the set of x values in the domain of both functions. That's the key thing here. So we just need to find the domain for each function individually, and then say, okay, which x values satisfy both of those domains? So first, let's look at f. Well, for f, we've got this square root here, so what's inside the square root has to be greater than or equal to 0. So x minus 3 has to be greater than or equal to 0, so x has to be greater than or equal to 3. And for g, we have 9 minus x needs to be greater than or equal to 0. So x needs to be less than or equal to 9. So it may help you to draw a number line for this. You may not need to. If you don't, that's fine. But if we look at this, what does this say? X is greater than or equal to 3. So this includes everything on the number line to the right of 3. And this is x is less than or equal to 9. So g is valid for everything to the left. But what we need is for both of these to be true. So this is where both are true. So the domain for these functions is given as the set of values between 3 and 9, including both 3 and 9. Now, that covers most of the situation, but we have to deal with f divided by g. So f divided by g is the same, except with the added condition that g of x cannot be 0. So we have to check that separately. So that means 9 minus x cannot be 0, which implies x cannot be 9. So that gives us the same domain almost, except we can't include the endpoint 9, so we use an open parentheses here. Okay, so hopefully that's pretty clear. All right, let's go ahead and move on to another definition. So this one is the operation on functions that tends to cause students the most grief, I would say. But actually, I think it's pretty easy if you make sure you just understand what this definition says really well. And then you'll find that composition of functions is really not too difficult at all. So hopefully between doing quite a few examples of this, you'll feel pretty comfortable afterwards. So if f and g are two functions, the composition of the function f with the function g is written as f composed with g of x equals f of g of x. Okay, what that means is, remember our order of operations says evaluate what's inside parentheses first. So what this means is evaluate g of x and plug your result into f. So there are a whole bunch of functions in the real world. In fact, I would say most real world functions are really compositions of functions. So for example, you might have a function, let's call this f1, that you decide, let's see, your mind tells you to push the gas pedal, and then the second function here is the gas pedal. How far it's pushed tells your car how far to accelerate. So what that means is my first input here is x, and then my mind has some function that, depending on my circumstances, tells me how far I want to push the gas pedal down on my car. And the result is that my foot gets pressed g of x into the gas pedal. And then that gas pedal, g of x, is pushed a certain amount, and the car, every car is going to have a unique function that decides based on how far and how fast the gas pedal was pushed down, how far or how fast the car is going to accelerate. And that's going to be your f of g of x. So that's basically what we're saying here, right? It's just like you're running two functions in a chain where the output of one function becomes the input for the new function. So let's take a look at these tables here and deal with a basic example here. So, and while we're at it, we're going to explore this idea that the domain of f of g of x is the values of x in the domain of g, for which g of x is in the domain of f. That sounds complicated, but let's just say it one more time. The domain of the composite function is the values of x that work for g, such that the output for g works for f. I think we'll see exactly what that means momentarily. So let's start with f of g of a. All right, so this is my table that describes my g function. So g of a gives me the output 2, so this is f of 2. And f of 2 gives me a, if I look at the table for f. Okay, that's nice. Now let's look at f of g of b. That's f of 3. And when I look at 3 on my table for f, f of 3 is c. And when I look at f of g of c, that gives me g of c is 4. So that's f of 4. And f of 4 is j. All right, now let's look at f of g of d. Well, g of d is 7, so this is f of 7, but there is no input 7 in the domain for f, so this is undefined, right? When we plug in an x value or an input value into a function that doesn't have an associated output, we say that that function isn't defined for that input, because that's what a function is. It's a defined rule that takes an input and sends it to an output. So here we're just saying there is no definition for what the rule should tell you to do when the input is 7, so this is undefined. Now we look at f of g of e. That's f of 8, and again, we look at the function for f, and there's no rule here, so we say this rule is undefined. Okay, so what is the domain in this example? Well, it's just A, B, and C. Because any other input for x inside the function leads to an output for g that doesn't work in f. So hopefully that makes some sense. Okay, so with that being said, let's take a look at these functions f and g here and evaluate some compositions. So f composed with g at 2 really just means f of g of 2. And what's g of 2? Well, g of 2 is 2 minus 2, which is 0. And f of 0 is just negative 6. All right, well, let's look at the general composite function, f composed with g of x. It's f of g of x. That really means f of x minus 2. So the key here to understand, to make sure you don't make mistakes, is that you're taking your original input x and you're replacing it with the entire output of g of x. So everywhere you had an x before, you have to have an entire x minus 2 now. So this is x minus 2 squared plus x minus 2 minus 6. So this is my composed function, but of course we're going to simplify this a little bit. So x minus 2 squared gives me x squared minus 2x minus 2x plus 4 plus x minus 2 minus 6. That's x squared minus 4x plus 4 plus x minus 2 minus 6. All right, now let's finally combine these. We only have one x squared term, so that's fine. This is negative 4x plus x, that's minus 3x. This is 4 minus 2 is 2. Minus 6 is negative 4. All right, so that is f of g of x. And of course, if you plug in the value 2 into this function, what should you expect to get? 4 minus 6 minus 4. So 4 minus 6 is negative 2. Minus 4 is negative 6. That's exactly what we would expect. So it's a little more work to find the general composed function. But of course, if you had to do many computations involving this function, in the end it would save you time versus computing each one separately. All right, so let's take a look at another example here. Given that f of x equals x cubed minus 2, and g of x equals 3x plus 1, find f of g of x, g of f of x, and f of x. All right, so let's start with f composed with g of x. That's the same thing as f of 3x plus 1. And that means I take my x in my function f and I replace it with the entire expression 3x plus 1 cubed minus 2. Now, this is a little bit cumbersome to compute, so I'm just going to write this off to the side. So 3x plus 1 cubed, that's 3x plus 1 times 3x plus 1 times 3x plus 1. I'm going to go a little quick here, so please forgive me. 3x times 3x is 9x squared. This is 3x and 6x plus 1. And then we multiply that whole thing by 3x plus 1. And then here, this is going to give me 27x cubed plus 18x squared plus 3x. And then that's going to give me plus 9x squared plus 6x plus 1. That was 27x cubed. Okay. Okay, so that gives me 27x cubed. And then I've got 18 and 9x squared, so that's plus 27x squared. And then 3x and 6x, that's plus 9x, plus 1. So this becomes 3x plus 1 cubed is 27x cubed plus 27x squared plus 9x plus 1 minus 2. Don't forget about the minus 2 here. And so simplifying that a little bit gives us 27x cubed plus 27x squared plus 9x minus 1. Okay, so now let's take a look at g of f of x. So this one means take the function g and replace its input with f, the entire function. That's x cubed minus 2. So here we're going to replace this x. So that's 3 times x cubed minus 2 plus 1. So this gives us 3x cubed minus 6 plus 1. That's 3x cubed minus 5. So right off the bat, this is something that I think is really important to recognize that's different about the composition of functions, which is that the order matters. Here, when we change the order in which we compose these functions, we get completely different results. That's not true for addition or multiplication. It is true for subtraction and division, of course, but for addition and multiplication, the order doesn't matter. For composition, the order always matters. The order that you compose these functions is very important. So keep that in mind and make sure you write that order in the correct direction. All right, so now let's take a look at f of x. So that just means take the function f and replace x with the whole function f. So it's just x cubed minus 2 cubed minus 2, right? Just replace your original x inside f with the entire function f again. Now, I'm not going to do this whole multiplication out. It's very similar to here, but I don't want to waste too much time on this video doing that kind of multiplication. So let's just go ahead and move on. All right, so find the domain for f composed with g of x given that f of x equals 1 over 4 minus x and g of x equals 1 over x squared. All right, well, let's see what we've got here. First of all, we need to know what the domain for g of x is. Well, the domain for g of x is simple. It's all real numbers except x cannot be equal to 0, because you can't divide by 0, of course. So this is the key thing. We remember when finding the domain of a composition, we look at the domain for g, and then we further restrict it by looking at what values cause problems for f when we plug g of x into it. So we start here. Okay, the domain for g. Now we look at the composition. We've got 1 over 4 minus 1 over x squared. So when we look at this, we have to think to ourselves, what causes us a problem in this composition of functions? Well, we can't divide by 0. So we take our denominator and say 4 minus 1 over x squared can't be equal to 0. So if I add that to the other side, I get 4 cannot be equal to 1 over x squared. I'm going to multiply x squared across and divide by 4. That gives me that x squared cannot be equal to 1/4. But if I take the square root of both sides, that tells me x cannot be equal to plus or minus 1/2. So that gives us our restrictions. So as I've said before, usually the most easy way to think about domains is to think about them in terms of restrictions first, and then write out the full set of valid x values based on that. So the domain for the whole composed function, f of g of x, is, well, we can't include 0, negative 1/2, or 1/2, right? So if you think about a number line, it's like you've just got an x over these spots. So how do we describe this? Well, we've got all of the values from negative infinity to negative 1/2, not including negative 1/2. And then we union that with all of the values from negative 1/2 to 0. And then we union that with all of the values from 0 to 1/2. And then we union that with all of the values from 1/2 to infinity. All right, there's 4 intervals for valid x values. So we just write this as the union of those 4 intervals. Okay, so now let's take a look at this function, or this composition of functions, f of g of x, where f is equal to the square root of x minus 3, and g is equal to the square root of 9 minus x. So again, we want to look at f of g of x, but let's start by looking at the domain for g of x. So the domain for g of x requires that 9 minus x be greater than or equal to 0. So 9 has to be greater than or equal to x. Okay, so now let's take a look at f of g of x. That's the square root of the square root of. So we're replacing x here with the square root of 9 minus x minus 3. So in this case, our input is now this whole expression. So what we need is the square root of 9 minus x minus 3 to be greater than or equal to 0. So that implies that the square root of 9 minus x is greater than or equal to 3. And if I square both sides, that implies that 9 minus x is greater than or equal to 9. So if I add x across and subtract 9 here, then I get x is less than or equal to 0. So again, let's take a look at the number line for these 2 restrictions, because now we've got to combine 2 restrictions together. So both of these restrictions must be true. The natural restriction on g and the restriction on f that occurs because we've plugged g into it. So what do we get here? X is less than or equal to 9. That's all of that. And then we get that x is less than or equal to 0. So if both have to be true, then the stronger condition here wins. X has to be less than or equal to 0. And so the stronger condition means the condition that's more restrictive. Both must be true, so we have to look at what restricts the x values the most here. In that case, that's this. So we would write this in interval notation as negative infinity to 0. Okay, so let's go ahead and move on to another topic here. The average rate of change of a composite function. So this is basically the same thing that we looked at before, and the regular formula is pretty obvious, I think. The average rate of change for f composed with g of x is just f of g of b minus f of g of a divided by b minus a. But one of the things I want to take note of here that you'll see that becomes relevant in calculus is that this happens to be equal to f of g of b minus f of g of a divided by g of b minus g of a times g of b minus g of a over b minus a. So, in other words, all we're doing here is multiplying by g of b minus g of a divided by g of b minus g of a, which equals 1. We've just written it in a silly way, right? We split up this fraction into f divided by 1 and 1 divided by b minus a, and we multiplied the top and bottom of each of those by this fraction g of b minus g of a divided by itself. So we're really just multiplying by 1, so we haven't changed the value at all. But what this lets us see is that the average rate of change of f composed with g is the same thing as the average rate of f from g of a to g of b times the average rate of change of g from a to b. So a way you could think of this goes back to that the car example I mentioned earlier. The average rate of change of my foot pressing the pedal times, so that would be ARC of G, my foot pressing the pedal, from the starting moment to the ending moment, times the average rate of change of the function that the car uses to determine acceleration, is the average rate of change of the actual change in acceleration of the car. So hopefully that makes some sense. So that becomes much more relevant in calculus, where we won't always be able to compute this part directly. But here we can actually compute this part directly for the example we're going to look at, so it's not as important. Okay, so let's take a look here. If f of x equals x squared plus 4 and g of x equals 4x minus 2, find the average rate of change of f composed with g of x as x changes from x equals -1 to x equals 1. So in other words, we want to evaluate f of g of 1 minus f of g of -1 divided by 1 minus -1. All right, so g of 1 is just 4 minus 2, which is 2. So this is f of 2 minus f of g of -1, that's -4 minus 2, that's -6, divided by 1 plus 1. Now f of 2 is 4 plus 4, that's 8, minus f of -6, that's 36 plus 4, that's 40, divided by 2. 8 minus 40 is -32, divided by 2 is -16. All right, well, that's it for that example. Let's take a look at one more. You work in a department store in which employees are entitled to a 20% discount on their purchases. In addition, the store is offering a 10% discount on all items. Let X represent the price of an item. Write a function, f of x, that models discounting an item by 20%. So the price of the item would then be 80% of its starting price, x. Right? So you're discounting 20%. 100 minus 20 is 80. In decimal notation, that's 0.8. And then for g of x here, we've got discounting an item by 10%. So that's just 0.9 times x. Now, for part C, it says use a composition of two functions from a to b to model the 20% discount first. So that means you're evaluating f of x first, because you're taking the 20% discount first. So your outer function is g of x. So this is g of 0.8x, which is 0.9 times 0.8x, and that's 0.72x. Now, D says use a composition of two functions from a and b to model taking the 10% discount first. So that would be f of g of x. So that's f of 0.9x. That's 0.8 times 0.9x. That's 0.72x. Which discount is better? They are the same. Now, you might say, well, Mr. C, didn't you say that the order matters for composition of functions? And yes, in general, it does. So for most functions, you should expect that, just like we saw here, when you change the order, yeah, it's going to change what you get when you compose your functions. But here, the two functions we were dealing with were only defined by a product of a number times x. So when we compose them, all we're doing is multiplying two numbers, and the order of multiplication doesn't matter. So since this particular type of composition of functions just results in a product of the two numbers, then the order doesn't matter here. On the other hand, if this was something like you had a discount where you took your price minus $5 and then another discount that was your price deducted by 20%, well then here the order is going to matter a lot. So if we look at this, this would be f of 0.8x. So here this gives us 0.8x minus $5 versus g of f of x, which gives us 0.8 times x minus 5, which gives us 0.8x minus 0.8 times 5, which is 0.8x minus 4. So what we actually see is that the discount here, the order does matter that you take the discount in. And that's because we're mixing these two different types of operations. It's not just multiplication each time, and then the order of multiplication doesn't matter. We're subtracting first, or we're multiplying by 0.8 first, and that changes the outcome of the composition. So that's something you got to be careful about. There are going to be times when you compose functions that you get the same value. And then there's going to be times when you compose them that they don't. So you should not assume that you will get the same value, because most of the time you won't. Okay, so hopefully that was pretty clear. And thanks for sticking around, watching the whole thing. Have a great day.